Big questions to start with.
Well, yeah. I mean, beyond just, living in them, what are they fundamentally? We just take them for granted, right?
We absolutely do. They feel like the background, the stage.
Exactly. Well, today we're doing a deep dive that really challenges that whole picture.
We are indeed. We're looking at something pretty radical in theoretical physics.
It's called the Quantum Vibrational Universe, QVU for short.
And it's an audacious proposal. Our mission today is to unpack how QVU basically flips the script on what's fundamental.
Flips the script how?
Instead of space-time being this pre-existing container where physics happens.
Right, the stage metaphor.
Exactly. QVU says space-time emerges. It comes into being from the relationships between everything else in the universe.
Wow. Okay. That's a lot to take in already.
It is.
So our sources cover the basic concepts, right?
Yeah.
The foundations.
Yeah, the conceptual basis, a potential mathematical structure, some really mind-bending ideas about time.
And crucially, the problems it faces, the challenges.
Oh, definitely. It's far from a done deal.
So for you listening, what's the really big idea here? Try this. Imagine your location, like where you are right now.
Mm-hmm.
Imagine that wasn't coordinates, not latitude and longitude,
Okay.
but instead it was just a property of all your connections. To everyone, to everything. Your place is your relationships.
That's a great way to frame the core shift in thinking. It's profound.
So to really get why QVU is so radical, maybe we should talk about the standard view first, the one it's trying to replace.
Good idea. So for centuries, physics has assumed space-time is fundamental.
Right. In classical mechanics, Newton's physics, it's just there.
Yeah.
Fixed background, absolute space, absolute time.
Exactly. Then with Einstein's relativity, it became more dynamic, curved by mass and energy.
The rubber sheet analogy.
Right, but it's still the underlying thing, the manifold, the container, even if it's a bendy one.
And even in standard quantum mechanics.
Yeah, typically we describe quantum states evolving against an external time t. There's usually some background space-time assumed. The arena is given first.
Okay. So QVU comes along and just throws that out.
Pretty much. It performs what the sources call an ontological inversion, which is just a fancy way of saying it flips what's considered fundamental.
It's an inversion.
The core idea is that the internal state of a system is fundamental. The sources use the term vibration as a kind of placeholder here.
Not literal shaking, though.
No, not like a guitar string necessarily. Think of it more abstractly for now. It's the fundamental quantum information defining what something is. Its essence.
Okay, so the vibration is fundamental. Then what about its location? Where it is in space and time?
That's the kicker. Location is not fundamental. It's secondary. It's emergent.
Emergent, like temperature from molecules.
Exactly like that. Location is derived entirely from the system's relationships, its connections, its interactions with all the other vibrating entities.
Whoa! So relations don't happen in space-time.
Space-time emerges from relations.
You have to pause and just think about that. It really does redefine what being somewhere means.
It absolutely does. It's a huge conceptual leap.
Does this connect to other ideas in quantum physics? It sounds a little familiar.
It does find inspiration particularly from relational quantum mechanics or RQM, Carlo Rovelli's idea.
Ah, right. RQM says a quantum state isn't absolute, it's always relative to an observer, another system.
Exactly. It gets rid of the need for this sort of God's eye view of the universe and helps resolve some quantum paradoxes.
So RQM makes properties relational, like spin is only up relative to the measuring device.
Yeah.
How does QVU extend that?
That's the crucial difference. RQM makes properties relational. QVU makes the location itself, the locus, relational.
The actual awareness.
The awareness, exactly. The universe isn't stuff sitting in space. The universe is the network of relations. And space-time is just our large-scale, sort of smoothed-out description of that network's geometry.
Okay, and this makes QVU more than just an interpretation, right? You said it's constructive.
Yes, that's a key point. RQM mostly reinterprets existing quantum theory. QVU proposes a new, deeper reality, a new ontology.
From which the physics we know should emerge.
Precisely. Both quantum mechanics and general relativity should, in theory, pop out as approximations from this deeper relational structure. It aims to synthesize RQM with ideas about emergent gravity.
Okay, let's dig into that core axiom. Vibration is location. What does that mean in practice?
It means location isn't coordinates, x, y, z, t. Location is the complete list, the full specification of a system's relationships with everything else.
And the vibration holds that information.
The vibration is the physical carrier of all that relational information.
Hmm.
The source uses a great analogy. Think about your position in a social network.
Okay, like on Facebook or something.
Right. Your position isn't your GPS coordinates. It's defined by who your friends are, family, colleagues, the groups you're in, how strongly you're connected.
And if I make a new friend, my position changes slightly.
Exactly. In QVU, an entity's location is just like that. It's defined by all its interactions, correlations, entanglements. Its vibration encodes all of that data.
So what if something had no relationships? Completely isolated.
Then, according to QVU, it would be placeless. Literally, it wouldn't exist anywhere in the emergent spacetime because it's not part of the relational fabric. Spacetime is woven from these connections.
Placeless, wow. So our smooth, continuous spacetime is, what, like a macroscopic illusion?
That's a good way to put it. We talked about emergence with temperature. No single molecule has a temperature, right? It's a collective property.
Right.
QVU says spacetime is similar. It's an effective description that emerges when you look at this underlying, discrete, quantum-relational network on a large scale. Fundamentally, reality might be more like a quantum foam or have an atomic structure made of these relations.
Okay, so if spacetime emerges, how does it emerge? What are the mechanisms? Does QVU offer specifics?
It tries to synthesize a few different existing ideas about emergent spacetime. One path is entropic emergence.
Entropic, like entropy. Disorder.
Sort of. Think information. People like Ted Jacobson and Eric Verlinde propose that gravity might not be a fundamental force, but an entropic one, arising from changes in information or degrees of freedom on some kind of holographic screen.
Okay.
In QVU, the vibrations could represent these microscopic degrees of freedom. Their collective behavior, their statistics, could create entropy gradients that we perceive as gravity and spatial geometry.
Interesting. What other pathways?
Then there's geometric emergence. This is closer to theories like loop quantum gravity, LQG.
I've heard of that. Space-time is made of tiny loops or quantum geometry, a spin network.
Exactly. LQG suggests space is fundamentally discrete, built from these quantum geometric units connected in a network. Or there's causal set theory, which views reality as just a growing set of discrete events with causal links.
And how does QVU fit in there?
Well, the vibrations in QVU could be the quantum states living on the nodes or edges of such a fundamental graph or network. The network is the space.
Okay, geometric. What was the third one?
Holographic emergence. This is inspired by the holographic principle.
From black holes and string theory, right?
Yeah.
The idea that information in a volume is encoded on its boundary.
That's the one. More recently, ideas like ADS-CFT correspondence, and especially the ER-EPR conjecture, suggest space-time geometry is actually knitted together by quantum entanglement.
Entanglement creates space.
In a sense, yes. So for QVU, the fundamental vibrations could be like qubits, basic units of quantum information. And the patterns of entanglement between them literally create the geometric structure, the distances, the shape of space.
So QVU is trying to bring all three together. Entropic, geometric, holographic.
Exactly. It's ambitious. It envisions this network of vibrating entities. That's the geometric part.
Those connections are defined by quantum information and entanglement. That's holographic.
Right, and whose collective statistical behavior gives rise to gravity and the smooth spacetime we see. That's the entropic part. It's a potential unifying framework.
How does it try to formalize this mathematically? You mentioned vibrations as vectors.
Yeah, the idea is that the state of a fundamental system is a vector in a Hilbert space. That's standard quantum mechanics language.
Okay.
But this Hilbert space has to be incredibly complex. It needs to contain the structure of the standard model of particle physics, the symmetry groups SU3 times SU2 times U1.
So an electron and a quark aren't different things, but different vibrational modes.
That's the idea, like different notes played on the same fundamental instrument. The challenge is showing how these specific modes and the standard model structure naturally arise from QVU's principles.
And interactions. They aren't just events happening in spacetime.
No, in QVU, interactions are the fundamental process. They're how the relational network updates. Dynamics isn't stuff moving through space. Dynamics is the changing pattern of relationships, governed by quantum amplitudes, probabilities.
So the universe is this vast vibrational network.
That's the picture. It's analogous to the spin networks in LQG. You have nodes,
The fundamental entities,
edges connecting them.
representing direct relations, interactions.
Right. And crucially, these nodes and edges have labels quantum numbers, like spin J, that quantify the nature or strength of the relationship. The state of the entire universe is then a superposition, a quantum combination of all possible ways to connect and label this network.
Okay, so we have this network, defined by relationships, quantified by quantum information. How do we get something as basic as distance out of that? This is where it gets really interesting, right?
It really does. There are two main ideas, possibly complementary. First, an algebraic path.
Like in loop quantum gravity.
Similar, yeah. You could define mathematical operators that act on this network state. Imagine a two-node separation operator. You apply it to the network, and it spits out a value for the distance between two nodes.
And that distance isn't just counting the links.
No, it would depend on those quantum labels on the edges along the path between the nodes. Maybe traversing an edge with a high spin label corresponds to a shorter effective distance. It implies distance itself is quantized, probably in tiny Planck units.
Fundamentally pixelated space.
Yeah.
Okay, what's the other path?
The information-theoretic path. This connects directly to the holographic principle and entanglement.
This is the one that clicked for you earlier.
Yeah.
Yes, it's incredibly elegant. The idea is that the emergent distance between two nodes in the network is inversely proportional to their quantum mutual information.
Mutual information. That measures how much two things know about each other,
Yeah,
including entanglement.
exactly. Total correlation. So if two nodes, two systems, are highly entangled, their mutual information is high.
Which means the emergent distance between them is small.
Wow. So things highly entangled are fundamentally close in this network, no matter how far apart they seem in our everyday space.
Precisely. It redefines proximity based on connection, not separation in an empty void.
This sounds like it could explain quantum entanglement, the spooky action at a distance.
It offers a potential explanation, yes. Think of the EPR paradox. Two particles created together fly light years apart, measure one, the other instantly knows. But in QVU, maybe it's not spooky. If those particles are maximally entangled, their mutual information is max. So in the fundamental vibrational network, their emergent distance is essentially zero. They're still adjacent.
So the spooky action is just an illusion created by looking at the large-scale emergent geometry.
That's the idea. It resonates strongly with the ER-EPR conjecture, which proposes that entangled particles might be connected by microscopic wormholes or Einstein-Rosen bridges. Here, the connection is the lack of emergent distance due to information.
And you said these two paths, algebraic and information-theoretic, are complementary.
Yes, the thinking is that the abstract quantum labels, the J spins on the network edges in the algebraic picture, are the very quantities measuring the entanglement or mutual information in the information-theoretic picture. It potentially unifies geometry from LQG with geometry from entanglement.
Okay, mine's slightly bent. If space-time emerges, what about time itself? How does anything happen? This is the problem of time, right?
That's it, exactly. Standard physics often relies on an external clock ticking away. But if time itself emerges from the network, you can't use an external clock. Change has to be described internally, relationally.
So how does QVU handle evolution?
It proposes a vibrational foam model. This is analogous to the spin foams used in loop quantum gravity.
Okay, spin networks are space. Spin foams are space-time history.
Roughly, yes. A vibrational foam represents a possible history of the network's interactions and changes. You can think of it like a higher dimensional graph.
What are its parts?
Well, you have 2D faces representing the world sheets of network edges persisting, 1D edges for the world lines of nodes, and crucially, 0D vertices.
And the vertices are the key.
The vertices represent the discrete interaction events, points where the network structure changes, where relations are formed, broken, or modified. The fundamental dynamics, the laws of physics, are encoded in the quantum amplitude associated with each type of vertex.
So you calculate the probability of going from one network state to another by summing up the amplitudes of all possible forms connecting them.
That's the path integral or sum over histories approach, yes. And it's dynamics without an external time parameter, because the time is implicitly encoded in the sequence of events within the foam itself.
Okay, no external time. But what about causality? What about the arrow of time, our feeling that time flows forwards?
Causality is built right into the structure. The connections within the foam define which events can influence which other events. It's inherent in the network's connectivity, much like in causal set theory.
And the arrow of time. Past, present, future.
That's not seen as fundamental in QVU. It's emergent, likely a thermodynamic phenomenon.
Related to entropy increasing.
Yes, but more specifically, it might be linked to the flow of information. As interactions happen, the vertices in the foam, the overall entanglement and complexity of the vibrational network tend to increase.
So the direction of increasing entanglement is what we perceive as the forward flow of time.
That's a strong possibility within this framework. Time's arrow is the universe becoming more relationally complex.
And does that mean there's no single universal time clock?
Correct. Each node, each system, would effectively have its own local, discrete time, defined by the sequence of interactions it participates in. These clocks would tick at different rates depending on how interactive a system is.
So my clock ticks differently from yours, potentially.
At the fundamental level, yes. Our shared, smooth, continuous sense of global time terre would be a macroscopic approximation, a statistical average over countless microscopic relational time steps.
Which neatly dissolves the whole problem of time. Time doesn't exist for the universe to evolve in.
It emerges from the universe's relational evolution. The universe builds its own history, interaction by interaction.
Okay, this is a truly grand, ambitious picture. But it must face some huge hurdles, right? What are the main challenges?
Oh, absolutely. The biggest one, arguably, is the recovery of the continuum. It's a massive technical problem, shared with LQG.
Meaning, how do you get our smooth, familiar 4D spacetime back from this discrete quantum network at the Planck scale?
Precisely. You need to show, mathematically, that the collective behavior of these network quanta reproduces Einstein's equations for gravity in the right limit. And why, specifically, 4 dimensions with the right properties, the Lorentzian signature, 3 space plus 1 time. That's crucial and incredibly difficult.
Without that, it's disconnected from experiment.
Completely. It remains a framework without a bridge to the reality we actually observe on large scales.
What else? You mentioned consistency earlier. If everything's relative.
Right, the problem of consistency. If all facts are relative to observers, like RQM suggests, how do we all agree on a shared reality? If location is relational, how do we establish consistent spatial frameworks between many different systems?
Is there a proposed solution?
The main candidate is decoherence. The idea is that systems are almost never truly isolated. They interact constantly with their environment.
Losing their quantum weirdness.
Effectively, yes. These interactions rapidly entangle a system with its surroundings, broadcasting information and washing out quantum interference. This leads to stable, effectively classical states and facts that all observers interacting with that environment can agree on.
But proving that works rigorously in this fully relational context is still needed.
Exactly. It's an ongoing challenge to show decoherence is powerful enough to guarantee a consistent macroscopic reality emerges from purely relative facts.
Then there's the particle zoo. You said vibration is a placeholder. How does QVU explain all the different fundamental particles we know?
That's a huge content problem. The standard model is incredibly rich. Quarks, leptons, bosons, 3 generations forces. Vibration sounds too simple.
So QVU needs to show how its fundamental Hilbert space naturally gives rise to that specific structure, the SU3 AU arrayed symmetries?
Yes. It needs to explain why we have electrons and neutrinos and quarks with the properties they have and the forces that act between them. Why these vibrational modes and not others? That's a defining challenge for any theory aiming to unify gravity and particle physics.
And the ultimate test for any science. Can it be falsified? Can QVU make unique, testable predictions?
That's the million-dollar question. To move from a compelling story to actual science, it needs concrete predictions.
Like what?
One possibility is Lorentz invariance violation, LIV. A discrete spacetime might mean the speed of light isn't perfectly constant, but could depend slightly on the light's energy.
Have we looked for that?
Yes, using things like gamma-ray bursts from distant galaxies. So far, the constraints are incredibly tight, meaning any LIV effect is very, very small if it exists at all. QVU would need to predict a specific, non-trivial LIV signature that's still allowed by current data. That's tough.
What about looking back at the early universe, cosmology?
That's potentially more promising. The dynamics of the vibrational foam in the universe's first moments would likely differ from standard Big Bang cosmology.
Leaving fingerprints on the cosmic microwave background.
Exactly. Or affecting the large-scale distribution of galaxies. We'd need to develop a quantum vibrational cosmology, QVC, to work out what those specific signatures would be.
Any other possibilities? Maybe something about quantum gravity itself.
Perhaps. Because spacetime emerges from entanglement, QVU might predict unique forms of spacetime noise, or maybe a different relationship between gravity and decoherence, which future high-precision experiments testing quantum effects in gravity could potentially probe.
So looking ahead, what needs to happen for QVU to mature as a theory? What are the next steps?
Well, first, theorists need to define the fundamental algebra, really pin down the mathematical structure of these basic entities and their symmetries.
Nail down what vibration actually means mathematically.
Exactly. Second, formulate the dynamics. Define that vertex amplitude, the fundamental rule for interactions in the vibrational foam.
The basic law of change.
Right. Third, and this is the huge one, tackle the classical limit. Probably starting with simplified toy models to see if and how smooth geometry can emerge.
Show it connects to Einstein's theory.
Yes. And fourth, explore cosmological consequences. Develop that QVC framework to derive potentially testable predictions for the CMB or other cosmological data. That might be the best route to making contact with observation.
So, wrapping up this deep dive, we've really journeyed into a radical reimagining of reality with the quantum vibrational universe,
It's definitely audacious, a universe woven not on a pre-existing loom of space-time, but from the very threads of relationship and interaction.
where space, time, geometry, even the flow of time itself aren't fundamental building blocks, but emerge from this deeper relational quantum network.
A universe that literally builds itself, interaction by interaction.
It leaves us with a pretty profound thought, doesn't it, for you listening?
Hmm.
If your location, your place in reality, truly is the sum total of your connections, your relationships, what does that imply about, well, about you? About identity? Maybe even consciousness or free will if everything arises from interaction.
What does it mean if your existence, your vibration, isn't just happening within space-time, but is actively contributing to weaving the very fabric of space and time itself?
It's something to ponder.